Hello, Connor.
Hello, William.
Hello and welcome to Physics.
I do love physics.
Physics, Unit A, I believe.
For the AS level.
For AS level.
Unit
stuff. 1. Yes, mainly for AQA, but you can use it for other units.
Pretty much.
Right, this is particle physics. I love particle physics. With me, Will, and Connor, our special...
very special.
Science specialist.
Woo!
Yay!
I live with a physics teacher, and my dad's an engineer, so I'm pretty much as physicsy as I can possibly be. And I'm rubbish at it, so we'll see how that goes.
Okay. We're going to get on with structure of an atom, aren't we, Connor?
Yes, we are.
Go.
Right, in the nucleus, which is the little tiny ball thing in the middle of an atom, you have the protons and neutrons. Protons have a +1 charge, relatively. Neutrons have a 0 charge. And protons and neutrons have roughly the same mass. There is a tiny difference, but no one really cares at AS level. And then orbiting around, like, massively, huge distances, it's unimaginable. You have the electrons, which are absolutely minuscule, 1/2000th of the mass of a proton, and they have a -1 charge. So, specific charge-wise, they are the most highly charged part of the atom. And if you consider the distances involved, if an atom was the size of our solar system, and say the nucleus was the sun, a electron orbiting it would be 6 times the distance from the sun to Pluto. It's huge distances. 99.99999% of an atom is nothing.
It's quite a big electron if the thing was the size of the sun as well.
Yes.
It'd be quite a big electron.
Yeah, okay, yeah. 1/2000, that's about the size of Jupiter.
Jupiter. That is...
I'm not going to say Uranus, that's just stupid.
You just said it.
Yes, I did.
You said Uranus. The structure of an atom. If you look at it, you have the chemical symbol, which defines what the atom is, what the element is, what it's made of.
Yeah.
And then you have 2 numbers. The top one is the mass number, and the bottom one is the atomic number, which also known as the proton number, I believe, which is the number of protons, which is subsequently the number of electrons, unless it's charged in any way. And then the top number, which is the mass number, is the sum of the protons and neutrons. So it's the nuclear number, which is the Z number. The nuclear number is the A number, which is the Z number plus number of neutrons. Thank you for helping me there, Connor. When I get all
just
confused.
chipping when I feel like it.
Yeah, okay.
We've also got, as I said, they don't really count the mass of an electron, especially from GCSE they don't count it at all, but in AS level they do tell you that it is 1/2000th. But as far as the numbers go, the nuclear number or the mass number, whatever, they don't actually count the electrons at all at this level. I'm sure they will.
Well, it is 9.11 times 10 to the minus 31, I believe.
That is the mass of an electron, yes.
Yes.
That sounds about right.
Just know, but you do need to know that it's in the data formula booklet.
I probably should know that off by heart.
Yeah. It's in the data formula booklet, so you don't need to know it. Right, anyway, back to atom stuff. If the chemical element, which is the big number, big letter even, or letters, is defined by the proton number, which is the bottom number. And the number of electrons determines the chemical nature of it and everything. But the number of neutrons can vary, which would mean you would make a what?
An isotope.
Wow, as in like topes, but all like iso.
No.
Yes, they're like isotopy. Anyway,
basically a different flavour of an atom where you have the same.
Different flavour.
It's an easier way to describe.
Different flavour.
Right, different weight then.
Where is my chocolate atom when I need it?
I want a strawberry one today, Jeffrey.
Strawberry.
No, I don't know who Jeffrey is.
If you could have any flavour of an atom, why would you go strawberry?
I like strawberry.
It's fruity.
Yes.
Health.
Right, moving on.
Health.
Moving on. Anywho. Different flavours or weights of atoms, they have the exact same number of protons, the exact same number of electrons in the same arrangements, but they have extra, or less in some cases, neutrons, which affects their mass, but not their actual charge or chemical properties.
My mind has been blown. Right.
Good.
Specific charge, we basically touched on that a little bit earlier, but it's defined by the charge divided by the mass. Therefore, the units are in coulombs per kilogram, or C kilogram to the -1.
Yes.
Basically, for that, it's pretty self-explanatory. All you have to remember is that if you're doing the nucleus, then you're basically doing the mass of the number of protons plus the number of neutrons, or the top number multiplied by 1.67 times 10 to the minus 27, because although there is a difference in proton number and neutron number, you don't need to put it into an equation at this level. You put that on the bottom, and then the charge is just how many protons if you're doing the nucleus, and that's it. Right, for the atom though, if it's got the same amount as electrons and protons, then specific charge would be zero, because it isn't charged, that's the point. But if you've got extra electrons or less electrons...
So it's an ion.
So it's an ion, yeah, then you basically get the difference, get the things they have extra. So if they got too little electrons, for example, then you have 2 times the protons. Yeah? Yep. Good.
Moving onwards.
Stable and unstable nuclei.
Oh, fun.
Ionizing radiation.
No.
That's the jingle for ionizing
No, there's no
radiation.
jingle.
Right, you go.
Right. What is radiation?
Ionizing radiation.
Oh, God. Right, there are 3 main types of radiation. You'll probably learn about at GCSE level. You've got alpha, beta, and gamma.
Beta? Beta? What is beta?
Beta.
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 Beta. It's the Greek. It's the Greek pronunciation.
Oh, can I have my strawberry atom and a beta atom? Oh, please.
This thing is a beta atom.
Beta.
No, you
particle.
That's fine.
Oh,
yeah, fine. Okay, no, I'll describe.
All right.
An alpha is basically a helium nucleus.
That looks very fishy.
Yes, the symbol for alpha does look like a fish. He's so witty. Right, the mass of an alpha particle is 4 because it's effectively a helium nucleus, which is 2 protons and 2 neutrons. Well, it is a
helium nucleus, though.
Okay, it is a helium nucleus.
It is a helium nucleus.
Right, okay. If I want to be corrected on technicality...
Do you know what I saw yesterday? Sorry to segue.
God.
I was in a restaurant yesterday going out for my sister's before she left to go back to university. And I said on the menu, on the pudding menu, it said, like, sponge and then drowned in coffee. But it didn't say that. It said... Sponge literally drowned in coffee.
Literally.
And I was just like, you can't. It's not literally. You can't have
it's not alive, and then you drown it.
Drove me mad.
I've seen one.
Drove me mad.
Bit dodgy, but I went to a restaurant.
Yeah.
Went to a restaurant here down. I think it was in London. I can't remember where though. But it was just on the burger menu, and it had. For all of you who have seen the film Brokeback Mountain.
Oh no.
On the menu, they were specified as a special burger, the Brokeback Burger, which was a firm hunk of meat between 2 firm buns. Now, for those of you who don't get that, go watch the film.
Stop.
Okay, moving on.
Stop it. Right, so yeah, the mass. An alpha particle is basically a helium nucleus.
No, it is a helium nucleus. It's not basic.
Shut up. A beta particle is basically a fast-moving electron.
Which, you got to be careful about beta and the electrons because it doesn't come from the outer shells of the electron. What happens is, I believe it's a neutron.
Neutron splits. It decays, yeah, that's better
into an electron and a proton.
So it's basically spat out of the nucleus.
Yeah.
That's what all decay is, basically.
It's nuclear radiation.
Yeah, well, thank you for that. Right, and a gamma particle has got no mass because it's basically a type of electromagnetic wave. Even though they're technically all waves because they are
wave particle duality.
We'll get onto that. That's like a whole load later. Right, we're running very late on, so I will speed this up. Basically, alpha slow, beta fast, gamma's very fast. Ionizing ability, alpha high, beta medium, and gamma
nothing.
Yeah.
Well, that
penetrating. It's kind of what? Penetrating power, alpha low, beta medium, gamma high. And stopped by alpha paper, beta aluminium, and gamma leads. That's
but even a foot of lead doesn't really stop gamma entirely.
Not helpful. It does for A level.
No, it doesn't.
It does for A level. I know it doesn't. It doesn't.
Fine, it does for AS level.
Stop it. You just stop. Right. Beta decay, the neutrino. The beta spectrum shows us that they can be emitted with a range of energies, don't they, Connor?
Yes, they can.
They can. This, therefore, is evidence for the neutrino, which has 0 rest mass and a 0 charge, which means
it's really a theoretical particle.
Yeah. You can't see it, you can't feel it.
Although they have proven that it does interact with stuff. Oh, sorry, just interesting segue here. Not segue. That is segue.
Segway? Segway?
I don't know. But there's a statistic where people like to throw around a lot, saying that 10,000 neutrinos pass through a person's eye every second on Earth, and they all come from the sun.
Shiny.
But some people have asked, very reasonably, why doesn't this cause any sort of damage or any interaction at all with the human eye?
Why doesn't this cause any sort of damage or interaction with the human eye?
It's because the neutrinos...
Well, William...
They only interact with the weak nuclear force, which we'll come on to a bit later.
They only interact with the weaklings in Hastings.
Because an atom is 99.9999 whatever, nothing. And the area around the nucleus, which experiences this weak nuclear force, is ridiculously small compared with the overall size of the atom. The vast majority
the vast majority
of neutrinos will pass through matter without having any interactions with anything at all, which is why people say there's 10,000 neutrinos through the eye every second, and that's true, but they don't actually interact with anything in your body. But something like 1 in 50 million will actually hit the centre of the nucleus, or glance off the centre of a nucleus, of an atom rather, and it will interact. And they've got this experiment in Iowa, I believe, in the States, deep underground, where they've filled like 1 million swimming pools worth of space with bleach. And every time a neutrino interacts with one of the atoms, it creates a bromine molecule, or it creates a certain atom. And then every 3 months, they filter out the entire pool and count how many atoms they've got of this certain substance. And that's proving the existence of neutrinos. They probably don't care, but... Anyway.
Or just that one scientist who's having a great time dropping an atom in every so often.
That would be really bad.
Just to be like,
interestingly,
oh my god, I think I saw one over there.
Interestingly enough, when they did this experiment, they predicted the amount of neutrinos they'd have every 3 months, and they found that it was only a third of what they expected. This was sort of 10, 15 years ago. And so this led to the sort of formation of the tau neutrino and the muon neutrino, which... Again, don't really need to know about tau, but muon we definitely have heard of. So anyway,
coming on to that in a little bit. Anyway, so so a neutrino is emitted with every nucleus decay. The main reason for that is that it's sort of cancel out the lepton number.
Pretty much,
yeah. Because you've got to have conservation of charge, baryon number, lepton number. Strangeness, unless it's a weak interaction, momentum, whatever else, different card. But lepton number is one of them. So if you have an electron coming out, or a beta particle, which is has a
lepton number
1,
you have to have
one, then you have to have -1 to cancel out. Therefore, a neutrino is emitted, basically, or an antineutrino with beta decay, or a neutrino with positron decay, which is just a positive thing. We'll come to that a little bit later. And you can do decays. Basically, if an alpha particle is spat out, you take 4 off the top number and 2 off the bottom number, if you want to do it easily. And if a beta particle is spat out, then you add 1 onto the bottom number.
Yep.
That's basically it. Because they're charges and so on and so forth. And yeah, that's all you really need to know. That's it for the first section of particle physics. Because it's such a long unit. Join us next time for more particle physics with me, Will, and him, Connor Durkin.
That's me.
Marks and Spencer's music to play us out, please.
Just put the music on over the top. It's fine.
Bye.